sampling rate conversion. What is the sampling rate conversion? Suppose we are given samples xn, which is obtained from a continuous time signal xc by sampling with sampling period t. And there's no aliasing when we do the sampling. Is it possible to obtain x prime that's samples of xc using a different sampling period? So here's xn. We obtain from xct by using sampling period t. And x prime is sequence obtained by using sampling period t prime. Can we obtain x prime from xn? One possible approach is to go back to continuous time. We can have a D2C going back to continuous time xct. If there's no aliasing, then we can get back xct completely, and then we can resample using t prime, then we can get x prime n, right? The question that we would like to ask here is it possible to obtain x prime n without going back to continuous time? Is it possible to obtain xn from x prime n from xn directly without going back to continuous time? Let's first answer the question, how are xn and x prime n related? If we can answer this question, then maybe we can solve the problem of getting x prime n from xn. We know x prime n can be obtained from xn by going back to the continuous time, then resampling, and do resampling again, we can get x prime n. So let's use this approach to understand how xn and x prime n are related, particularly in the frequency domain. Suppose this is x ej omega. It's been limited to pi over 2. When we go back to the continuous time, then we know this is how xc would look like. It would be, if it's been limited to pi over 2, then it's been limited to pi over 2t. And if the height here is 1, the height here would be t. As an example, suppose t prime is t over 3. In this case, what would x prime ej omega look like? Should it be a squeezed or a stretched version of x ej omega? It should be a squeezed version, right? If x is been limited to pi over 2, then x prime is been limited to pi over 6. And the height here will become 3. Since we are using a smaller sampling period, we know x prime n would have more samples than xn. Let's consider another example when the sampling period is larger. Let's say t prime is 2 times t, then this is what x prime will look like. It is now a stretched version, and the height here would be half. In this case, x prime n has fewer samples than xn. So when sampling period is smaller, x prime t prime is smaller, x prime is a squeezed version of x, and when sampling period is larger, x prime becomes a stretched version of x. So how can we do this? Is it possible to do some kind of processing so that the spectrum will get squeezed or stretched? To answer this question, we will introduce 2 new building blocks, expander and decimator. An expander is also called a upsampler. We have a box, and in the box we have an arrow pointing upward, and an integer L. L is a positive integer. For example, L is equal to 2, L is equal to 3. And here's how the output is related to the input X. The output XE is equal to X n over L when n is a multiple of L, and it's 0 otherwise. Let's look at an example. For example, L is equal to 3, and this is X. As sample 0, 1, 2, 3, and L in this example is equal to 3. So if we look at the definition, it says that the output is non-zero only when n is a multiple of L equal to 3. So it's non-zero only at 3, 0, 3, 6, 9, and so on and so forth. And minus 3, minus 6, and so on and so forth. So the output XE, it could be non-zero at 0, 3, 6, 9. And what is the value of XE when n is equal to 0? It is 0 divided by L, so it's X0. And what is the value at n equal to 3? It will be 3 divided by 3, so this is X1. And when n is equal to 6, this will be X. 6 over 3 is 2, and this one is X3. So the samples of X0 comes here to 0, and the samples of X1 comes to 3, this one comes to 6, this one comes to 9, and all the other samples are 0. For all the other n that are not integers, they are not multiples of 3, those samples are 0. So what an expander does is really inserting zeros. And when it inserts zeros, this XEN has more samples than the input. So the expander increases the number of samples by inserting zeros. And we will see how this is helping with the sampling rate conversion later. To see how this can be of any help for sampling rate conversion, let's go to the frequency domain. Let's see how X and XE are related in the frequency domain. So let's write down the Fourier transform of XE by definition. This is the Fourier transform definition. The summation n here is for all integer n, but then we know XE is non-zero only when n is a multiple of L. So we can say n should be an integer multiple of L, so we write it as LK for all k. So now we can sum over all k, and n we replace it by LK and L times k here. Okay, and we recognize that XELK is really just XK, right? Because XELK is equal to X, this number divided by L, so this becomes K. And this looks very much like the definition of Fourier transform for X, right? Except one thing. If this were omega, then this will be the Fourier transform of X. But instead of omega, we have L times omega here. So this is XEJ L times omega. So this is how they are related in Fourier transform, as simple as that, a frequency scaling. All right, when we have a frequency scaling, it could be stretching or it could be squeezing. Which way is it here? Stretching or squeezing here? XE is a stretched version or squeezed version of X. Remember, L is a positive integer, right? So which way is it? XE is a squeezed version of X. Let's look at an example. Suppose this is X, the familiar triangle spectrum, XEJ omega from minus pi to pi of one period here, and the height here is equal to 1. And let's say L is equal to 3, so XE is XEJ3 omega. So we squeeze the spectrum of X by 3. Pi comes here, becomes pi over 3, and this is minus pi over 3, and this is XE, right? Is there something else? How about here? and here. Would it be just 0? Well, if we want to look at these two frequency regions, what we are really asking is what is here, right? And here, because XE is a squeezed version of X. So what comes here, what comes in this region will be from here. And this part will be squeezed to here. So should X be, if X is 0 in this part, X is 0 here, right? Then this part will be 0. Is this true? Not really, right? Because X is periodic, so it cannot be 0. Here's another copy here, and here's another copy. And these two copies will get squeezed. And so here we have one copy, and here we have another copy. And the height will be just the same. Now if we have L equal to 3, X prime, XE, EJ omega, we have more sample than X, and it's a squeezed version. So this should correspond to the case that the sampling period gets smaller. In the sampling rate conversion, if we want the sampling rate to become smaller, T prime is T over 3, then X prime is a squeezed version of X, right? It's a squeezed version. This is X, and it's a squeezed version of X. But it's squeezed in the way that this will be 0 here, and it's 0 here. Now let's go back to the output of expander. So X prime N should have a spectrum that look like a squeezed version of X EJ omega, and it's 0 here and here. And the copy of X EJ omega is squeezed to pi over 3 and 2 minus pi over 3. And all the others are 0, and the height here will be 3. So how can we get from XE to X prime EJ omega, the desired X prime EJ omega? If we can simply filter out this copy and increase the height 3 times, then we are done. So let's do that. This is called an interpolation system that increases the sampling rate. We take the output of the expander and we pass it through a ideal low-pass filter. It has cutoff frequency pi over L, and the height is L. Then we can filter out, like what we have said, only one copy and raise the height. This HI is what we called a interpolation filter. The ideal low-pass filter has impulse response like this, a sinc function, sine pi n over L divided by pi n over L. And this interpolation filter plays a role similar to reconstruction filter when we do D to C conversion. For example, we have an XCT here, like so. It's a function of t, and we take samples at 0t, 2t, 3t, then we get xn, 0t, 2t, 3t, then these are the samples that we get. If now the sampling period is 1/3 of t, then we have x prime n. In addition to the samples of xn, we have samples from here, samples from here, samples from here. And so we will get some extra sample. With the expander, what we get is XE. It has samples of XN at 0, 3, 6, 9. It's multiples of 3, but the samples in between 0, 3 are zeros, and these are zeros, these are zeros. From what we have discussed so far is that by passing this XE through this interpolation filter, we get the output which is equal to X prime of n when the samples are taken with sampling period t over 3. So by passing this XE through the interpolation filter, we will get x prime n. And that means the filter hi plays a role interpolating these samples. So these zeros now have non-zero value, and these are the interpolated values by passing xe through the interpolation filter. We call this connection of expander and interpolation filter an interpolation system. It's the interconnection of the two. Now going back to the problem that we start with, is it possible to obtain x prime n without going back to the continuous time? Yes, indeed, we can do this by using the interpolation system.